Thank you.
If I can get this bar out of the way. Okay. Are you seeing my screen?
I'm seeing this meeting is being recorded.
Yeah, I see everything.
Oh. You should see a blue screen says basic electronics.
I'm not seeing that.
Yeah, I just see like the computer screen.
Oh, okay.
I see you, and then this meeting is being recorded.
All right. Let me start to share again. How about now?
Oh, yeah, I see it.
But I still have the meeting being recorded thing on top. Oh. Okay, now I got it, Robert. I'm with you.
Okay. Internet must be slow in Texas.
Probably.
All right. So we're going to talk a little bit about resistance and power. And first, about conductors and insulators and why they're different. A little bit more about the free electrons that we talked about last time, which is how energy and charge is actually moved around. Look at some of the particular elements that we use, like copper and silver, silicon, things like that. Get into what resistance is and what Ohm's law is, which you will use a lot, how you measure it, and then get into actual power and power measurement. So when we talked about the atom models, and we talked about the outer electron shell or orbit, depends on which model you use. It's called the valence shell or the valence energy band. And the electrons in that valence band can be number anywhere from 0 to 8 electrons. If there's 1 to 3 electrons in that outer shell, it's classed as a conductor, and it means that those electrons are very easy to separate. Basically, they don't require a whole lot of energy in order to become a free electron, and then they can go fill in a missing spot or a hole in another atom, and that causes that charge to move from one place to the other, and the virtual hole to move in the opposite direction. And also it transfers energy, because you have to increase the energy of that electron for it to actually be able to break free and move. When it recombines with another atom, it's back to its original energy level. So that difference in energy has to go somewhere. It either goes to energizing another electron to cause it to move, or part of it can go and generate heat. In some cases, it could generate photons or light, or some, spectrum of all of those things. It could even generate what's called phonons, which is low frequency energy, which you normally see as heat or vibration. So that's where the resistance part comes in, is how much of that energy is actually going to generate heat. So the harder it is to move those electrons around, depending on the material, the more energy it takes, then there's more energy to generate heat, which is why resistors dissipate heat, just like your standard light bulb, which is essentially a resistor, has a tungsten filament, which is a fairly high resistance. Takes a lot of energy to cause those electrons to move, so that gets converted into heat, which causes the filament to start glowing and actually at some point emitting photons. On the other end of the scale, we have insulators, which are atoms that have between 5 and 8 valence electrons. And it becomes very hard, takes a lot of energy to separate or to energize one of those electrons to make it a free electron so it can move. And we tend to use those kind of materials to separate conductors. And that's why we call them insulators. Some of the examples, we typically use things like mica and glass, quartz, even silicon itself, if it's pure, which happens to be one in the middle, it has 4 electrons, is a fairly decent insulator. It's used as the base material when we talk about semiconductors. The best conductors, at least of all the simple atomic compounds, silver is the best, followed by copper. Not quite as good, but it's a lot cheaper than silver, and it doesn't tarnish as much. Followed by gold. It's not nearly as good a conductor, but it has the advantage of it doesn't oxidize. So we tend to gold plate connector pins, things like that, to keep them from oxidizing. Any questions so far?
Not on my end. I'm good.
Okay. And I know Shay wasn't here to talk about all the free electrons and stuff. So is that going over your head or?
No, I'm good so far.
Okay. There's a little chart I found showing, if you look over on the right-hand side, the way conductors are, the red down there, the valence band, is the valence energy. These are energy levels. And you see what they call the conduction band, where those electrons are free to move. They actually overlap. And you see a thing called Fermi level. As I understand it, and I'm not going to try to go into a lot of physics, it's a probability that at the Fermi level energy, the electron has a 50-50 chance of being above or below. And that starts to get into all the quantum theory, which we won't talk about at all. But it becomes a lot of probabilities. When you have a semiconductor, where we've got essentially 4 valence electrons, there's a separation between the valence energy amount and the conduction band energy. And we'll actually see that as a threshold voltage when we talk about semiconductors, p-n junctions, where it takes in the case of silicon, 0.7 volts actually cross that threshold. In the case of an insulator, and these aren't necessarily scaled, there's a wide band gap between the conduction band and the valence band. And if you put enough energy or voltage on that insulator, it will, in essence, break down and carry some current, but it takes a tremendous amount of energy. Okay, so we tend to use metals because of the fact that they can conduct charges and energy. And they have, depending on the metal, like silver, has very little energy loss that gets converted to heat. And we tend to use the non-metal materials as insulators to separate conductors so we can control the path of electrons. Here's your standard periodic table. And if we look at what they call transition metals, you can see that's where copper and silver, gold, mercury, platinum, all those kind of things we think of as normal metals are all in those yellow boxes. And they have varying degrees of conductivity. If we go look at the green boxes, and I think they call those basic metals, which is your aluminum, gallium, indium, tin, lead. And that's what solder is made of that we use to make connections between connectors and components. It's a mixture of tin and lead. Some of those others never heard of. Livermorium and moscovium are all recent discoveries. And we get up to the light blues, which they're calling semi-metals. And these are what we actually use to make semiconductors. Silicon being the most basic one. But we have things like boron and arsenic and antimony, phosphorus that we use to what we call dope the silicon to give it a positive or a negative charge. Basic intrinsic silicon is essentially an insulator, has no charge. We can add material like boron or phosphorus and make it either have a net positive or a net negative charge. And that's how we make semiconductors, by junctions of that P, what we call P and N, or positive and negative materials. Okay. Any questions on the old periodic table?
Not on this end, Robert. I'm fine.
Okay. So we said conductors were metals that had 1 to 3 valence electrons. Silver is the best. We typically use copper for most things. A lot of times you'll see aluminum, particularly in things like antennas, where it has to be outside. It's lightweight. It doesn't corrode as much as copper. And this is what this is called the Bohr model, named by Niels Bohr, where at that point in time, they believed that an atom had this nucleus of protons and neutrons surrounded by shells of electrons, and each of those shells was a different energy level. And there's some formula on how those shells are populated, and I can't remember it off the top of my head. But you'll notice in the case of silver, the outer shell, called the valence shell, only has 1 electron, which is why it's a very good conductor. It's very easy to supply a small amount of energy to get that electron to move to a higher energy level and become what we call a free electron. So it can, at some point, combine with an atom that has a missing electron, or in some cases, just add another electron into this outer valence shell. Copper is a slightly smaller atom. It still has one valence electron, so it's nearly as good a conductor as silver. And the other thing that, if you remember from your high school chemistry physics, the number of electrons is always equal to the number of protons. So there's always a net charge on the atom, unless it loses or gains an electron, and then it either becomes positive or negative net charge. We look at iron, which isn't a great conductor, but it's actually a conductor. It's used quite a bit because of its strength. It has 2 electrons, so it requires a little more energy. Therefore, you see a little more heating as a result of the energy being passed through it. So when we talk about resistors, those are materials that have 3 to 5 valence electrons. So your semiconductor stuff is kind of in the middle of that too. These are materials that aren't very good conductors, but they're not very good insulators. Typically, we use things like carbon film, different metal oxides to actually manufacture resistors. In some cases, we use wire, like nichrome or tungsten wire, but we don't normally use that for any high frequency stuff because of the inductance, which we'll get to later. And tungsten is, well, I guess they're still using tungsten or some tungsten alloys for light bulb filaments in the old-fashioned light bulbs. And there's our tungsten, but it's a very large, heavy atom. It has 2 valence electrons. We look at carbon. It's kind of like silicon. They're very similar, which a lot of the science fiction books, we have silicon-based life forms as opposed to carbon-based, very similar atoms. It has 4 valence electrons. It also allows it to form a crystalline structure, which we see in the case of like graphite and things. In the case of insulators, like I said, those were materials that had between 5 and 8 valence electrons. Oxygen turns out to be a pretty good insulator. It's all around us. Nitrogen is also, so the combination of the two doesn't conduct electricity very well. But this is one of the things that when Shay gets more interested in the weather and the propagation and ionosphere, it's the oxygen and nitrogen molecules up in the upper atmosphere that get hit with ultraviolet rays and other things coming from the sun that energize those valence electrons and actually create free electrons and ionize the ionosphere, which is where it got its name. And there again is nitrogen. It's slightly higher with 5. And then we have semiconductors, which are those kind of weird things in the middle. In most cases, we use materials that have 4 valence electrons. Most things, except for very special purpose, are going to be based on silicon. In some cases, we still use germanium. But in order for it to work as a semiconductor, we actually have to add impurities to the crystals. So when we grow a silicon crystal, we add like boron or phosphorus, like I said before, to convert it to a positive or negatively charged material. This is just showing for a P material, it's basically a material that has excess holes or missing electrons. In the case of an N material, it's got an excess of electrons that are bound in the crystal. There's our silicon with 4. It tends to make it a nice symmetrical crystal because these 4 electrons can I want to say mate, but connect to other silicon atoms, and you wind up with what they call covalent bonds. So it makes a nice symmetrical crystalline structure. Germanium is slightly larger, but it also has 4, so you get the same kind of a crystalline growth with it. Boron is one of the impurities that we use to make a, let's see, boron. It's got 3, so we're going to have a positively charged material because it's going to have an extra hole. Phosphorus is one of the common ones used to make N material because it's got 5 electrons. So when you add that to the 4 in the silicon, it disturbs the crystal and you wind up with free electrons bound in the crystal matrix. So what do we take away? That metals are good conductors. Because they have a lot of free electrons. It doesn't take much energy to cause them to move from one atom to another, which is what we define as current flow. We use them to connect electronic components together. And we use things like glass, rubber, plastics, for insulators. Mica is one of them. It's used a lot because there's essentially no free electrons, and it takes very high forces or voltages to cause current to flow through an insulator. Any questions on that one?
No, I'm good, Robert. Thank you.
Okay.
I'm good so
Shay?
far.
All right. Now, if I remember